Hello, hello. I would like to talk a little bit about the Iceland situation now. I was recently invited to the Geo Days in Finland, in Turku, and I gave a little talk about sampling lava throughout an eruption, high resolution sampling, as we call it, and what this may reveal. I was talking about La Palma, but given the current situation, I will focus on the Iceland part of that talk, not the La Palma part. And I want to give you a quick summary of what I said there. And we'll go through the history of the Reykjanes eruptions in the recent cycle, and then say a few words about the Sundhnúka eruptions that are going on right now. So let me share my screen. And here it is. So you should be able to see that now. And let me just get organized here. So this is, of course, from the 21 eruption, this image. And as I said, high resolution sampling of volcanic eruptions, reasonably small scale eruptions by the standards of, for example, supervolcanoes. Both the La Palma as well as the Iceland eruptions are comparatively small scale. But the problem is, of course, not the scale. The problem is that they occur in relatively densely to medium densely inhabited areas, and that's why they cause a lot of damage. But let's go into that first. A few words about Iceland. Iceland sits, of course, on the Mid-Atlantic Ridge, and the Mid-Atlantic Ridge is quite a sophisticated and very long spreading system. And Iceland is one of the few places where the ridge is above sea level. And of course, that poses the question, what's going on in Iceland? What makes Iceland special? Now, there the plates are spreading with about 2 centimeters a year. And Iceland, nevertheless, has an extra helper, geologically speaking, and that's the Iceland plume that sits underneath, and that is pushing up. And this is why Iceland is actually above the ocean surface. So in Iceland, we have the northern volcanic zone, the mid or western volcanic zone, and we also have the eastern volcanic zone and the Reykjanes volcanic belt, RVB, here on the map. And this is here. And I'd like to talk, of course, about that. This is where the plates are spreading, and we'll come back to the plume a little later. So it's often characterized as a leaky transform fault. So it's not just plates drifting apart like this. It's actually, they're doing this. They have relative motion. And when they do this, there is little openings. You know, you see between my hands, there can be a little opening here where I can look through now. This is where magma would then rise up. It has an oblique shear component, if you will, and this is the real reason for this. And this is also why the volcanic systems there in purple and now the young volcanic field at Fagradalsfjall is actually spread out in this northeasterly, southwesterly direction. Now, you have heard this before, I'm pretty sure. It's been through the media and through the literature. The Reykjanes volcanic belt has multi-cyclicity. There has been eruption periods of intense eruptive activity almost all along the peninsula, and they were interrupted by pauses of up to 1,000 years, 900 to 1,000 years. And this was happening several times, 3 times before. And now we have the Fagradalsfjall eruption, which is now 2000 of our time calculation. And this means it might be the 4th of such cycle we see in the geological record. And given that now we have the Svartsengi one here as well, yeah, it looks like that we are in for a more serious eruption period there, and it could actually last years to decades, that we have more eruptions potentially all along the peninsula if this extends further. Now, let's go into the more recent events. In March 21, the Meradalir eruption started, and it started off with some several 100-meter long fissures. And in April of that year, 4 craters formed, and they all emitted lava, but this reduced rather rapidly, and eventually one crater was the dominant one. And here we see the crater row in the map. So the various numbers here give the occurrence of the craters. And vent number 5 was the one that proliferated, and here is an image from early in the eruption. There you see vent 1, vent 5, vent 3, etc. Vent 5 being a rather small one here, but by the end of eruption it looked more like this. Vent 5 was yeah, the dominant one, and it was overshadowing some of the others. So this is the images there. There was a lava lake in that vent, and it was repeatedly overflowing, and it was actually starting to be cyclic, certainly in summer of 21. And we published this in a paper by Radu et al. And here we show one of these sequences. This is drone footage that Daniel did, Daniel Müller. And there we have the vent, and it starts to rise, the lava level starts to rise, and eventually it flows over. We have a lava flow coming out, and then it starts to go down again. And then just a few minutes later, literally a few minutes later, it starts to rise again, and it fills up the level of the lake, and it fills to the brim, and then it flows out, and then it goes down again. So spectacular events and really puzzling. We are suggesting an explanation in our article, but yeah, there may be other explanations. In any case, there was spectacular drone footage, of course. This is again from this period, looking into the crater lake that is overcrusted here. There's one point where lava was poking up before the rise again occurred, and then it would pour out towards the right in this image and create these lava flows. Eventually, the lava flows were so voluminous that they were spilling into Meradalir, which is up here, and they were also spilling into Nathagi Valley. The night pasture is a very protected valley, and there we have the arrival of the lava in that part of the area. And here, spectacular scenery with these new black lavas going over the hills down into the valleys. And here's a little video, and I hope it works. You can see Nathagi Valley here, and the actual eruption site is up there in the hills. And this is a time sequence, and this is actually in June of 21. So let's see, here we go. This is, of course, sped up, so it's very fast, but here you see the lavas filling the valley. And now the extension of the lava is not as rapidly anymore, but the lava is inflating. So there's lava being pushed inside, and this is causing the inflation, but also degassing. So it's a combination of new lava flowing and degassing. And the two processes work hand in hand, because the degassing creates actually voids and spaces where new lava can migrate. So this is the sequence, very rapid. And I can do it once more. So just for your visual pleasure, and I'll have a sip of coffee in the meantime. So, and oops, now we need to move forward. This is it. After the 21 eruption came to an end in September that year, it took about a year, and then the Meradalir eruption started just in the valley where some of the lava from 21 has been flowing. This is the very start of the Meradalir eruption. Again, it was a fissure. Here you see the fissure, and the fissure was cracking into the hill here. So there's several small vents along the hill, and some of it was then forming lava flows going down into the hill. But again, eventually one cone was becoming dominant. This is this one here, and this is actually the tip of the fissure. This is up the hill now. So here we can look into a little baby volcano that didn't grow big, and I afford you a little look into there. So this is the very end of the fissure. So you can look into this little hole there, and this is a tiny little spatter volcano that didn't grow any further. But as I said, The main vent then developed here in the center of the valley. There were several smaller ones to start with, but by mid-August, there was only one active, and this is this one here. And of course, we went out to sample this. And we were learning a lot about how to sample and how to avoid certain mistakes. And here we see the Meradalir valley filled with new lava. The red in this image here is the new 22 lavas, and the yellow here is the 21 lavas. For most part, the 22 lavas follow on 21 lava, but there's one tiny bit up there where we actually have lava covering new ground. But here's a little video. Let me show you this. This is a flyover, and this was sent to me by Annemieke van Röckel, and she had the luxury of flying over the eruption, and she shared the video with me. Very grateful for that. Thank you. So that was very instructive, I thought. And oops, we need to go forward. This is the place here at the far end where the 22 lavas is actually not flowing on 21 lavas, where they cover new ground, expanding the lava field at Fagradalsfjall. And up here, that's this very point, and this is the tip when you approach it from up here. And of course, we were sampling all of this. And sometimes you end up in a very peculiar situation like this one here, and you realize that lava is coming, flowing on the older lava, then you quickly go out. This is 21 lava that we have sampled in 22, and just an hour later, it looks like this. The new lava has arrived. So just sit there, have a cup of tea, and wait a little bit, and then you can actually sample the new lava. So you can sample 2 years in one go. And indeed, this is us doing exactly that. This is when the new lava then arrived. Then we had samples from different years here in that particular spot. And of course, this is also the last chance to sample some of the 21 lava, at least for some time, because once it's covered, it's going to be very hard to get to. So then Lithli-Hrutur, again, almost a year later, July 17th, a new eruption started up here in Lithli-Hrutur. This is this hill here, and there was a vent starting to come up here, the lava flowing downhill. Eventually, it covered some of the other lava, but for most parts, it was flowing on uncovered ground, uncovered in the sense there's no lava from the last few years. So a big cone developed, the Lithli-Hrutur cone as we call it now, and this is the cone here. And this is before the lava pond developed to the west of it. Initially, it was draining to the south towards the Meradalir area, but eventually there was also draining towards the west. There was a fracture developing, and initially, as I said, it drained to the south here, but then the fracture here ruptured the wall of the cone, and a little block fell out, creating a pond of lava afterwards. And then this was flowing to the west a little bit, but then continued to flow to the south. On the map, this is this part here. It's flowing to the west and then to the south. So when you look at the vent from below, like you do here, it looks impressive, but it's not quite as spectacular as looking from top. This is now a drone video that Will Moorland from the University of Iceland has kindly made available. So let's have a look at this. So this is how it looks when you look inside. It's really a bubbling and boiling pot of lava in there, and quite spectacular. And some of the things, they look like little fountains shooting out when you look from below, but it's more impressive when you look at it from above. And here it's draining towards the south, and later this part broke out, and then it drained also to the west. So this is now down in the Meradalir Valley, and there we have the 23 lava flowing on the 21 lava, and this is my colleague Lucas here taking a few pictures. And here, obviously, we are missing the 22 lava. So this is, if you will, an incomplete stratigraphy. And this is a few pictures here, close-up shots from that event. And here further down in the valley, in Meradalir Valley now, here's the wall of 23 lavas approaching on 21 lavas. That's how it looks in detail. And eventually the 23 lavas flowing on the 21 lavas is approaching the 22 lavas, the dark ones here. Let me get you to see that a little better. So here you are. That's the 23 lavas from Lithli-Hrutur. That's the Meradalir lavas that flow down this valley. And all of them is actually flowing or has been flowing on the 21 lavas. Eventually, of course, the 23 lavas met the 22 lavas and covered part of it. And there's one place that I was showing on the map, this place here, where all the three lavas are resting on top of each other in proper stratigraphic order. And here is us going to this particular spot. As if we had hunted a lion, being very proud that we are at the one place where the stratigraphy is entirely intact. Now, we sampled all of these, of course, for our geochemistry, and this is very important. There was a bit of a game changer. We learned a lot about how to sample, and eventually we also learned that we need to protect ourselves better and better. This is the colleagues from the University of Buffalo, and they inspired us with their space suits, and eventually several of these equipments were employed. It also had a kind of a bit of a volcano fashion effect, because while the sampling videos that we had on YouTube before were attractive to people, once the spacesuits came into play, the whole thing took off, and it created tens of millions of views on YouTube. So very much appreciated for all of those following us. So this sampling, of course, created a beautiful sample set that allowed us to go at the geochemistry in detail. And I'll go a little bit into the geochemistry now. I'm keenly aware that not everybody out there is into geochemistry, but a little bit of it. So this is our 22 paper, Bindeman et al., which we published about less than a year after the eruption ended. So very proud that we were so rapid with it. So here what we see is timeline plots on the left-hand side. There is several timeline plots, and initially there was a change in chemistry quite strongly, and then it plateaued out. So this gave rise to speculations that there could have been different mantle components involved in the eruption. And here we have some ratio plots for incompatible elements. And here we see also the time marked in different colors. So there has been some changes. But the other takeaway point here is it's not an N-MORP, it's not an upper mantle derived magma. It is more like a plume type magma, as we've seen here, the Iceland array, and here's the OIB, the Ocean Island basalt field. That is plume derived usually, and the samples plot a lot closer to that and overlap with the plume field. Again, here's OIB, here's N-MORP, and we are moving more and more towards the OIB, towards the end of the eruption. And that implies that the plume plays a considerable role here. So this is just to zoom into this. There was, of course, discussion about how this works exactly. Could be tapping of distinct mantle sources, mixing of distinct mantle melts, or the mantle melting at various depths sequentially throughout the eruption. And this was noted by our team, but also by the other team that was working on the geochemistry, led by Sami Haldursson. They published theirs also in 22, just a few weeks after our article came out. They had an article where they show the reference data here for the Reykjanes Peninsula and other places in Iceland, and they show that the 21 lavas are shooting off there. This is only the first 50 days, but there is a dramatic change as well, and this is therefore pretty firm. So we found it, and the Haldursson team found it as well. So how you interpret that, that's a slightly different thing. But if it's mantle components, we thought at the time that's very interesting, because there's this big debate about in Iceland where the low oxygen isotope signals come from. So here is delta 18O oxygen isotopes, and here in central Iceland, here the Holleraun eruption, and here Grímsvötn in yellow and Laki in orange. There's relatively low numbers. Mantle Atlantic MORP, for example, plots at 5.5. These values are below mantle. fractional crystallization can only bring the values up, so something else is going on. And if it's really different mantle components, we thought we can test whether the mantle is one of the sources for the low delta 80No. This plot here is from Troch et al. This is to discuss low delta 80No magmas. So this is mantle, and this is the various trends that fractional crystallization will produce. So anything below mantle is really unusual and requires a special explanation. Our samples plot round about here for the mantle. That's the result. And indeed, our Fagradalsfjall samples throughout time didn't really show a lot of change and are extremely mantle-like. So this is really intriguing. And here's our timeline. So it goes off here. There's a mild variation here, but otherwise it's very stable and not a lot of changes. So if these initial changes were mantle changes in the mantle source, the implication would be that these mantle sources do not come with different oxygen isotopes. So this raises a big question mark for how to explain the central Iceland ones. And it seems almost that crustal processes are the more likely origin then. So we published this in June 22, and this was really about 3 weeks or, well, 3 to 4 weeks before the Meradalir eruption came. So, of course, one of the key questions we had after publishing this paper was, does it continue? And this is unpublished data. We're working on an article, but the Meradalir data do continue the trend. And of course, Lithli-Hrutur and now Svartsengi, they're in the pipeline as well for the analysis. So it seems that the trend is continued. However, having said this, there was increasing evidence that maybe this initial change in the major elements could be something else than mantle. And this is again from Meradalir et al. This is barometry and water content measurements in that paper. And here we have barometric results, crystallization pressure of kleine pyroxene crystals, and they all crystallize between some 2 to 5 kilobars, and this translates into depth of about 6 to maybe 15 kilometer, and that's actually a little too shallow for the mantle. So the magma was certainly stored and crystallizing in some way for some time in the crust and is not just a pure mantle melt. This led us to this model at the time, and this is an important model because it shows that there may be different mantle components that could be depleted as well as enriched ORB and dip components, as the geochemists might want to call them. But we also have a mush area here somewhere in the crust, and this is likely the source for feeding upwards. Now, how does this all link to Svartsengi and the Sundhnúkar eruptions? Well, we all know that from December onwards last year, there was new eruptions in the Sundhnúkar area over here. And this is a swelling area. It's depicted in this graph here. And this swelling area gave rise to a series of small eruptions. One is ongoing just now in March, in late March of 24. And one of them actually reached the town of Grindavik here. The lava barriers that have been put up have been enormously successful. Most of the lava was diverted, so a real engineering feat, but also a very costly one, I have to admit. So the construction of the lava barriers was extremely costly, but they are effective if one is prepared to invest and put the time and resources into this. So a quick word, is Svartsengi or the Sundhnúkar eruptions different now from Fagradalsfjall or not? It's a question I got very frequently. Is this the new system or not? Well, the reality is that if you look at the timeline, this is for potassium over titanium oxide. There you see this initial change at Geldingadalur. This is the Meradalir eruptions, the Lithli-Hrutur eruptions, and this is from December last year. We got the data in just very recently, and this was only a very short eruption. This is why the data plot on top of each other. There's a mild change, but it's not different to, for example, the Geldingadalur eruption. These ratios are a bit like, they have significance. If the magmas are of different origin, these ratios tend to differ, but we can plot it up here against MgO. This is the initial change here, and then this is Meradalir. This is Lithli-Hrutur, and the Svartsengi seems to continue. So there's a bit of an arch here in that plot, but this is a continuation. There's one Geldinga sample plotting up here, and there's one Meradalir sample plotting out of context. Well, this is normal in a way. We always have an outlier, one or two. This is not uncommon. So in fact, actually, if there is no outlier, I get a bit skeptical. So this is a normal way. But statistically, most of the data fall into these trends. And here, these Svartsengi Sundnúkar data seem to confirm this. So the first interpretation would be that we're dealing with a similar magma source that has fed the Fagradalsfjall and now also the Sundnúkar eruptions. This is now confirmed with mineral data, and Lucas from the Czech Academy of Sciences, he just had a little paper published in the Czech Polar Reports. I made a video about this, and here is a SEM image, a scanning electron microscope image from the Lithli-Hrutur eruption. Here's a few more images of the Lithli-Hrutur eruption. Here's olivine and plagioclase being the main dominant larger minerals in there. And here is a discrimination plot for trace elements in olivine. It comes from Lucas's paper. And here we have the Geldinga-Dali, the Meradalir, and the Lithli-Hrutur fields. They're slightly distinct. They seem to form sort of an evolutionary trend. And if we look at the Sundnúkar data, the phenocryst, the larger crystals, they plot here, and the microphenocryst, the small olivine crystals, they plot here. But overall, there seems to be a trend. So this is very comforting news, and it goes along with the hand specimen evidence of larger plagioclase in there. So there seems to be a fractionation trend being the main process at work here, rather than a lot of new magma or genetically different magma being involved. And here's another plot from Lucas's work. And this is manganese over zinc. And here we see that the trend seems to hold true for these other trace elements. And in fact, this diagram is indicative for the type of mantle that's involved. Here we have peridotite, here we have pyroxenite mantle, and it seems to be more strongly dominated by peridotite. So this is very instructive, and now the big question is, how does it look beneath the Reykjanes? Here on the left, this was the very early model. Everything is mantle derived. There may be a mantle reservoir, and then now we're looking more towards crustal systems that may rise up, feeding Fagradalsfjall and going to the left as well. And here, this goes back to earlier work for previous eruptive cycles on the Reykjanes Peninsula. There was a speculation of a large reservoir potentially in the lower crust underlying the entire peninsula. Now, the issue with this model is, if this is true, then we could have multiple eruptions here coming up, and there may be an eruption here, there may be an eruption here. It may be rather unsystematic, and they could rise up rather rapidly. So if this is true, then we have one system, and it will feed several eruptions at different times, and the eruptions are likely small, and the magma is connected, and we have a little bit of inflation of shallow reservoirs here, but once the overpressure is let out of these shallower reservoirs, the whole thing will die down. If this model is correct, then we're in for quite a show, because it might mean we could have multiple eruptions along the entire peninsula. So from what I understand from the character of the eruptions, also from the geochemical data that we have now investigated, this seems to be the most likely eruption scenario or supply scenario for the magma. It's not just purely mantle fed, and it's a somewhat larger reservoir, likely on the Fagradalsfjall, that feeds upwards as well as laterally. Certainly that's consistent also with the earthquake patterns. I don't think we're dealing with this scenario here, but having said this, if the situation at the Reykjanes Peninsula continues for years or decades, this may become a reality. So this is not out of the question, but it's not what we're seeing right now. So I would then say, because we are probably dealing with option D here, we are probably okay for now. It's not going to be too bad, but of course we have to think about more eruptions, small eruptions in the area for quite some time. And this brings me to the end. I say thank you for your time, and then yeah, here a little kind of rock that was still kind of hot when we picked it up, and the volcano behind it. If you have questions, you are of course extremely welcome to leave questions here in the message box. I will also encourage comments and leave a link to our paper, the Meradalir paper, and the recent report in the Czech Polar report, so that you can read up if you like. So thank you very much, and I hope you found this useful, a little summary, a brief summary of the eruptive events and also of the current geochemistry, because a lot of people on YouTube asked me, what is the chemical results? So I felt I'll put a little effort in and share that with you, not just with the people at the conference in Finland where I've just been, but also with YouTube here. So thank you very much for your time, for your interest, and for all the questions. Keep them coming. I enjoy talking about volcanoes, as you figured. So, and it looks like I might have a chance to go to Iceland in the next few days. Let's see about that. So all the very best and good luck. Bye-bye.